Piece of paper, right? Plain piece of paper. I feel like I'm doing a magic trick. Plain piece of paper. Okay. Question. If I wanted to put this back together again, could I? I mean, I'm not talking about difficulty. Is it possible? Is it possible for me to figure out how to put these pieces back together again? Or how they should be oriented? And if I could go down even to the molecular level, could I put it back together again? What about now? Has your answer changed? No? So if you think yes or no, I would argue at the molecular level, if I was that small, I could. It might take a while, it might be difficult, right? But I could put it back together again. Now? If you've got an opinion, you've got your opinion, right? And your opinion pretty much stays the same no matter how much I do this. Let me ask you a question. Let's suppose that there are little molecules in here called paper. There was a Pa somewhere on your an element of paper. That's it. A Pa is on your periodic table. These are Pa atoms all in a flat sheet. And I keep separating them, right? As I tear it smaller and smaller, what is the stuff in my hand made out of? Yeah, paper atoms, or if it's diatomic, it's paper molecules, right? If we're going to pretend that there's such a thing as paper, an element of paper, and I have a sheet of paper atoms, then as I tear these smaller and smaller, until we get to the place where we become subatomic, right? As I'm tearing it, I continually have paper in my hand. Okay. Actually makes sense that it would be a paper molecule, not atoms, but so they're all molecules of paper in a flat sheet. But, so if I take this and tear it again, still paper, right? Paper, paper, paper. Paper molecules. However, not quite enough. Can I put that back together? Why not? Okay, I burned up what was paper. Let's talk about that a little bit more. What has become of my molecule of paperness? Is it paper anymore? It's something other than paper, okay? We'll talk about these two major categories of change. The first one is physical change. Physical change is when I take something and in our example here, like paper, I take it and I rip it. I haven't really done anything to it other than changed its appearance. Okay? So it's a physical change in that the atoms or the molecules that make it up don't change. All that changes is its appearance. Went from a nice big sheet to all these little jagged pieces. But I haven't changed what makes it up. That stays the same. It just looks different. Physical change. Second one is a chemical change. The chemical change is my burning. As I take the flame and I burn the paper, I'm actually converting the molecules. In this case, molecules of paperness have turned into something else. Now I can't just put it back together because physically it's changed too. You see the physical change that's happened? It's darkened and now it's withered up. It's not the same process to put it back together as before. But something more substantial has happened. Those places that have actually experienced the heat, a chemical reaction has taken place, and what used to be paper molecules are now something else. something other. I no longer have pure paper molecules. I now have paper molecules, the part that's not burned, and those parts that are burned are something other than the paper molecules I had before. And so that is a chemical change. I've changed the structure of the atoms or molecules in the sample. So if you look on page 208 in your book, they do the same thing there. They have a big pile of ash, okay, a burning ash actually, and torn up paper. And they use the same example that I've used. If I take paper and I tear it up smaller and smaller and smaller, but I keep tearing it, I still have paper. I've changed the way the atoms and molecules look, but it's still the same stuff. Chemical change, I burn it, I convert it into something else. So those characteristics again, physical changes, the product looks different, okay, and that looking different could be a lot of different things, okay, but it basically looks different. Chemical changes, the products are different. You've converted it from one thing to another. You've taken the atoms and the molecules, you've broken them down, and you've rearranged them in a different combination. You've made a different combination from the same building blocks, from the same atoms you had before. And also physical changes are easily reversible. And when I say easily, I mean relatively easily. Putting together a piece of torn paper is not easy. But compared to reversing the burning of a paper, it is easy. It's much easier to go down and try to get those fibers to be back joined at the right place than it is to recapture those escaped gases, bring them back, convert them backwards, a backward reaction into paper. It'd be like unburning the paper. You burn it with a positive flame, you unburn it with a negative flame. If you could do that, it would be just a simple physical change, but it's not. You've converted it into something else, and once it's converted, it's much more difficult to reverse it. But chemical processes are reversible. They are. It's possible in many cases, in some cases. I won't say many cases. In some cases, it's possible. Matter of fact, if we get this far enough in this book for the year, we'll find that some reactions are continually going back and forth, back and forth, back and forth, finding a place of equilibrium. But those are the two major changes, physical changes and chemical changes. Physical, think of it as primarily a change of appearance. Chemical, you've fundamentally changed what you're looking at from one thing to another. So on your own, 6.1 says, classify these changes as either physical or chemical changes. Let's think about them together. Okay, steam condenses. Is that a physical or a chemical change? What's happening? Does everybody know that vocabulary? First of all, what is steam? Somebody want to wow the class and tell us what is the definition of steam? Go ahead, wow me.
Water in its gas form.
Gaseous state, okay. So it's in a gas phase. We'll learn that word in a minute. But a gas phase, it's water in a gas phase. And when it condenses, what is it doing?
Turning back into water.
Turning back into, it's water when it's steam. It's not turning back into water.
A liquid form.
It's turning back into water in a liquid form. Good. So condensing something is to take it from a gas phase, steam, to a liquid phase, which we generally call water, but it's liquid water. So when you're changing it from gas to a liquid, is that a physical or a chemical change? Right, because what's the chemical formula for steam? H2O. What's the chemical formula for liquid water that you drink? H2O. What's the chemical formula for ice? H2O. Okay? Those are physical changes. Those are phase changes. We'll talk about that soon. But those are physical changes to water molecules in relation to other water molecules. Okay? Gasoline burns. There's a hint there, isn't there? Do you know anything else we talked about maybe burning?
No.
No? Okay, time to wake up. Okay, gasoline burns. Physical or chemical?
Chemical.
Mr. Answers today. It's chemical, right? Because you're starting with something, and we'll find out more detail later on when you'll have to balance this reaction equation. But it's a combustion, so you're taking something, and you don't need to know this yet, but for combustion, you're taking a fuel, you're adding oxygen and heat, like your fire triangle, right? Adding oxygen and heat. Heat is the energy to cause a reaction. Burning is nothing more than the energy causing the reaction. And when that reaction takes place, it releases gases which are combustible, so the heat ignites the gases. It's a self-perpetuating cycle. But you're taking gasoline and you're adding heat to it and oxygen to it to burn it. And the products of that are something other than gasoline. You don't fill your car up with gasoline and then put a collection device at your exhaust pipe so you can recollect the gasoline to reuse it, right? It's something else. It's carbon dioxide or carbon monoxide and water vapor. It's a chemical change that takes place. Third, you get your hair cut. I need one. I need a couple of them cut. Okay? Is that a physical or a chemical change? Physical. Like the paper, I'm tearing it. Here I'm taking, not me, somebody hopefully more competent than I am, takes scissors and clippers and cuts my hair. So it haven't changed the structure chemically of my hair, just changed the way it looks. You don't go to get a haircut and have someone, put like a hat on you and pour liquids or light anything on fire or things like that. Well, maybe some of you do, but for the most part, we don't do it that way. Get a little singy. It makes it hard to brush it out for those of you that brush your hair, okay? So for the haircut, it's just a physical change. Now, souring milk. Is that a physical change or a chemical change? Okay, I have a physical. Other opinion? It's chemical. What's actually happening when milk sours? The little bugs that live in the milk, right? They are eating the milk, and like all living things, when they eat food, they expel waste, okay? They produce chemical changes in the milk. And when you taste sour milk, you're tasting that change in the milk. It's no longer the same molecules that it was before it soured. The living organisms in there that have soured it are changing them. So living organisms are causing chemical reactions to take place in the milk, and what you taste as that sourness is the change that's taken place. So it's a chemical change that takes place. Physical change in milk would be, I put it in the fridge and the cream floats to the top, so I can skim off the top that cream to make ice cream, and I've got skim milk left over. That's a physical change. Okay. Sugar dissolving. When I take sugar and put it in water and stir it up, it's a physical change because the sugar doesn't break down into something else. As a matter of fact, we'll do this later. We'll take salt. We'll dissolve a whole bunch of salt in some water, and then we'll boil off the water. And guess what will be left? Salt, right. Which means it didn't change in anything else. It just now has water surrounding all the molecules of, in this case, sugar. So the water surrounds the sugar, and because there's water around every molecule, it appears to disappear. But it hasn't chemically changed in anything other than sugar. Milk is poured. Physical change. It's in one container, it's poured and moved to someplace else, but it's still milk. It hasn't chemically changed into anything else. And iron rusting. Okay, I've got one of each. Anybody have a third opinion?
Neither.
It's a chemical reaction. What's happening there is iron is changing into iron oxide. So what was, now it's not pure iron, but let's say that a nail is pure Fe, the element iron. When it rusts, that rust that's on the surface usually gets exposed to water. Oxygen from the water and the iron atoms react to form ferrous oxide or iron oxide. Okay? And so rust is actually chemically different than iron. It's more than just, it does make a physical change, but that physical change is because of a chemical change that's taken place. So it's primarily a chemical change, right? Chemical changes often do have physical characteristics to them, but they're not primarily purely physical change. They're a chemical change that results in a physical change. Make sense? So it's kind of both. Physical changes don't include chemical changes, but chemical changes can include a physical change. Looks different. Like the burned paper looks different. That's a physical characteristic, but it's a chemical reaction that causes the physical change. All right. So we've already spoken from the corner, 3 different phases of matter. There is a 4th phase. What phase is that we're not including for this class? These are the 3 most common. Most everybody knows these 3, but there is a 4th phase of matter. It is plasma, okay? So plasma is the 4th phase, but we're not going to include plasma in our discussion for the scope of this course. We're just going to stick to these 3 primary phases. solid, liquid, and gas. Okay. And like most things, we tend to think of one substance as the primary. And for human beings, we tend to think about water. I can't speak for any other creatures on Earth, but we tend to use water as our example. But water is an exception for some things. So you need to know the exceptions for water, because most people think in terms of water. Because we just used already about steam condensing, right? We were thinking in terms of water. The steam is the gaseous phase of H2O. It condenses down into the liquid phase of H2O, and there still is a solid phase of H2O, which we haven't talked about yet. But those are the three primary phases: solid, liquid, and gas. Think about ice, liquid water, and steam. Okay, so a phase change. It's when a substance changes from one phase to another. So it's starting off as either a solid, liquid, or gas, and it's becoming either a solid, liquid, or gas, but something other than what it was. It's converting from one form into another form. So let's, again, think about water. For our discussion now, it'll work. Let's think about this phase change where we go from a solid to a liquid. What do we call it when we go from a solid to a liquid? Well, to go from a solid to a liquid, let's think about it. We take solid to a liquid. What we're going to do is I've used red arrows to show increasing energy. We're going to add energy to it. This will all tie together either today or tomorrow. But we have something that's solid. We add energy to it, and in the process of adding energy to it, it becomes a liquid. What do we call it when water, which is ice, becomes water that we drink? What is that process of change called? Right, it's melting. Okay. When a solid changes phase to a liquid, we say that the object melted, right? If I put something on a table, I put a flame on it, and you see it go, "Boo." What happened to Frosty? He melted, right? Okay. What about going the other direction? For these, I use a blue arrow. And that's to indicate that energy is being taken out. Energy is being removed. It's the opposite of adding energy. So when I heat something up, that's generally how we think of adding energy, just like with a flame, okay? When I add heat to ice, it melts and becomes liquid water. When I have liquid water and I take heat out, it turns into a solid. Well, that process is known as freezing. Right, so we've got melting and freezing taking place. Melting and freezing is the process of phase change between solid and liquid, depending upon the direction you're going. From a solid to a liquid, it melts. From a liquid to a solid, it freezes. How do we go from a solid to a liquid? We're going to find out more detail later, but we add energy to the solid to make it into a liquid. How do we change it from a liquid to a solid? We take energy out of the system, and it freezes. Okay? So any questions on that? Cool. We'll finish the module tomorrow. Just kidding. Just kidding. Okay. So there's generally a place here we call the melting point. The melting point is that point where the phase change starts to happen. And we're going to find out later that it's not like we start adding energy and there's this perfect direct relationship between energy and temperature. Okay? The melting point, what's another name for the melting point? If it's the melting point because that's where it melts, what could this also be called? The freezing point, right? What's the difference between the melting point and the freezing point? The direction you're traveling. Okay? But the melting point refers to a temperature. It's that temperature at which one phase begins to change into the other phase. Here's one of the really unique things that we've already spoken about a little bit in here. I believe we referred to it already. When I've said to you before, if you have a bucket of ice water and you have a soda in the ice water, what temperature is the soda? 32 degrees Fahrenheit or 0 degrees Celsius or 273.15 Kelvin, right? It's going to be those temperatures. Why? Because if it was any warmer, all of the water would be liquid. And if it was any colder, all of the liquid would then be solid, right? If it was colder than 32 degrees Fahrenheit, 0 degrees Celsius, then all of that liquid would already be solid. And if it was any warmer, all of the solid would already be liquid. The fact that you've got both phases at the same time means you're at that point. You're on that point. And the freezing point melting point of water is the 32 degrees Fahrenheit, 0 degrees Celsius. Okay. And what's happening there? If I start adding energy to solid ice and it begins to melt, you see the temperature's rising, 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 then the temperature's going to hold steady for a while until all of the solid becomes liquid. And then the temperature's going to start to rise again. The energy required for the phase change holds that temperature at that freezing point, melting point. Okay? So the phase changes from solid to liquid or liquid to solid are depicted here on the board. Are there any questions on that? Because we're going to go to the next phase change, which is from liquid to gas. When we add energy to a liquid and it changes phase from a liquid to a gas, think about water. What do we call it when liquid water changes into gaseous water? Boiling or evaporating. Okay, boiling or evaporating. When we're talking about adding direct heat where we're making this change quickly, it's generally boiling. And when we move from gaseous back to liquid, as was referred to in the problem earlier, that physical change that takes place, moving from a gas to a liquid, is known as condensing. See, as I'm taking the gas and I remove energy from it, it condenses and changes from a gas back into a liquid. If I have the liquid and add energy back into it, it's going to boil and, through the boiling process, evaporate and turn back into gas. So, from solid to liquid, liquid to gas, there's one other phase change. Is anybody familiar with it? Now, again, we're not talking about plasma, so we're leaving that out of the discussion for now. But solid, liquid, and gas, the phase changes between those three. We've done solid to liquid and liquid to solid. We've done liquid to gas and gas to liquid. What else could there be? Oh, I forgot the boiling point slide. There you go. The boiling point, same as talking about the freezing point. It's that point at which, when water is boiling, what's its temperature? It's 100 degrees Celsius, 212 Fahrenheit, right? 373.15 Kelvin. It's boiling at that temperature. Temperature's going to rise till it gets to that point. It's going to stay at that point until all of the liquid is gas. And then it's theoretically possible, if you've captured the gas, to heat it above once all of the liquid has become gas at the boiling point or condensing point, depending upon the direction you're traveling. But we have a change that goes from a solid directly to a gas. Skips the liquid phase altogether. So we're adding energy to the solid and it sublimates to become a gas. Now, the most common sublimation that you may be aware of, we're not going to test this one, okay, but it's a carbon dioxide fire extinguisher. Has anybody seen one of those things go off? Yeah, you probably did it, right? Yeah, maybe. Okay. So what happens when you squeeze and use the funnel and you are squeezing a carbon dioxide extinguisher? What comes out the end? It looks like a white foam, right? It's not really like soap billows, but it's more like a little styrofoam kind of looking stuff, like the season now is Christmas, so you can make a Christmas scene or something like that by spraying around. Don't try it. But if you spray the carbon dioxide on the carpeting, here's what really cool things. When the carbon dioxide is gone, is the carpet wet? Just think about it. Carbon dioxide comes out of the fire extinguisher, and it's solid carbon dioxide. What's solid carbon dioxide known as? We have a familiar name for it. Well, CO2, but what's the common name? Just like H2O is called water, CO2 in a solid form is known as dry ice. What happens to dry ice as it warms? Okay, last year the musical, right? We had dry ice backstage when Sydney was up there with her cackling being the witch and the Wizard of Oz. We had a solid block of dry ice back there, and yet from the audience, what did it look like? Fog, right? It went from being a solid to being a gaseous suspension. It didn't form a puddle, and then from the puddle form a gas. It went from the block directly to that gaseous fog that came out in the set. So when you spray carbon dioxide on the floor, when the carbon dioxide goes to room temperature, what phase is room temperature carbon dioxide at? Let me ask you a question. What do you breathe out? Carbon dioxide. Are you breathing out solid carbon dioxide? Everywhere you go, like, oh, all those cubes are falling out of your face? No. Some of you, it looks like you exhale liquid that's just drooling, right? But it looks like, but for most of us, when we exhale, it comes out as a gas. So we breathe, we yawn, and we let our neighbor breathe it in. And we're sharing this gas back and forth among us, this carbon dioxide, right? When you spray a carbon dioxide fire extinguisher on the ground, it goes from being at that temperature and pressure, which allows it to be a solid, it's now in a new pressure, atmospheric pressure, and a new temperature, room temperature, at which it should be a gas. And it goes from being a solid directly to being a gas. It doesn't go through the liquid phase, which means the carpet doesn't get wet, right? Because it's never has liquid carbon dioxide on it, because the carbon dioxide went straight from solid to gaseous form. Okay. Plus, if you use a carbon dioxide extinguisher, you've got the dual effect of the solid smothering effect to keep the oxygen out. Plus, when the flame heats up that that fire extinguisher, it converts it into carbon dioxide. What does fire do in the presence of carbon dioxide? It goes out. It's looking for oxygen, not carbon dioxide. And so you smother it physically, and then when it changes into a gas, you smother it chemically. So, anyhow, part of this whole thing about the different phases, and part of my statement about carbon dioxide in the form of a foam, like a extinguisher, going straight to a gas is this. And this is probably peculiar to me. I think this is a really cool concept, but it's a really important concept that you just have to remember, okay? If someone asks you, for example, is iron a liquid, a solid, or a gas? Your response is all of the above. Or your response is, I need more information. Why? Because every single element can be every single phase. Everything that's on the periodic table and everything that's built out of things that are on the periodic table can be at different pressures and temperatures, solid, liquid, or gas. We tend to think of them based upon the phase that they're in at room temperature. Okay? So if I were to ask you, like for example, just in the way I said, what do you call liquid H2O? You said water. I said, well, actually, it's all water, right? Yeah, well, kind of. We don't often refer to solid, ice as solid H2O or solid water, but it is. So I get that. In a vernacular kind of a way, we tend to think of it in the state it would be at room temperature. I mean, if I were to ask just about anybody in the school to draw a picture of water, very few would draw a picture of a cloud, and very few would draw a picture of an ice cube. Most people would draw a glass of water, a drinking fountain, a pond, a river, something like that with liquid water in it. We tend to think of everything in terms of how we experience it at normal living temperatures and pressures. But what we experience is not the typical range in the universe. There is a much broader range of temperatures and pressures than we experience. And so, for example, you can't assume that because I'm on this spaceship made with aluminum that I'm always going to be inside of a solid spaceship. Because if I fly a little bit too close to that sun and my spaceship turns to liquid, I'm in trouble, right? I mean, there's not going to be any last-minute transmissions or return flight. I mean, it's over for me. Because as soon as the aluminum spaceship turns into a liquid, guess what happens to me? I'm turning into a gas. Because at the temperatures and pressures that will turn aluminum to a liquid, most of the things that make me up go into a gas. Unless you remember that you're like primarily water, okay? So we don't do really well above the boiling point or the freezing point without some kind of protective devices. We just don't, doesn't work too well for us. Okay. Also, just as you think about yourself as an individual, please realize that I believe the number is 80%, but 80% of the cells in your body are not human cells. So that's a little bit more for biology than it is for chemistry, but kind of put a context on the whole thing. You are mostly non-human. And what you consider to be you, like inside your skin, is mostly not human. So, question to you is, are you an individual or are you a community? Okay? So see, you got a lot more responsibility. You're not just looking out for yourself, you're looking out for everything that you're carrying around with you. Anyhow, going back to chemistry, every single element and every single compound can exist as a solid, liquid, or gas given the right pressure and temperature combinations. So if I put something under very low pressure or very high temperature or both, things that I think of as solid could suddenly become gases and evaporate in front of me. Conversely, things that are normally gases could become solid. I share this every year, so forgive me if you've heard it already, but one of the most one of the science fiction stories that I read as a young person that impacted me a lot with regard to science was a story about, and it was about, back then it wasn't global warming, it was global cooling. The world's going to die because everything's going to freeze, okay? Thinking has changed in the last 30-something years. Okay, but back then everything was freezing. We were looking for the next ice age to hit us. And so there's a science fiction story about a young person who survived a cataclysmic temperature shift, and all of the gases in the environment solidified and fell like snow. Because the temperature changed gradually, different combinations of chemicals fell at different times. And so one of his daily chores was to go and dig through the layers to find the layers of oxygen so they could bring back buckets of oxygen back to where they lived and melt it so that they could breathe. You know? So I still remember that as, wow, that's really weird. I always thought of air as a gas. Well, not under all conditions. All the gases that we breathe can become liquids and then solids given different pressures and temperatures. And so I will refer to this quite often. It is an important concept for you to understand, that something is not a liquid, a solid, or a gas based upon what it is. It's based upon what are the conditions it's in. Okay? Not what it is, but conditions in. It's kind of like saying before, metals or nonmetals. For some reason, we tend to think of metals as solids within the range that we live, you know, copper, zinc, all these things that we make stuff out of as metals. And we tend to think of the nonmetals as gases, nitrogens, oxygens, chlorines, fluorines, right? That's not always the case. You can have liquid or even gaseous metals, and you can have solid and liquid nonmetals. That's just where they tend to be at the temperatures and pressures that we live at. That's where we tend to know them. So, the main difference between phases of matter is the volume they occupy. That's one of the takeaways at this point, the second section on phase changes. The main difference between phases of matter is the volume that they occupy. Because most substances, with the exception of water, so if you remember that water is the exception, remember water and then think backwards, okay? That's the way I learned some things. So most substances, except for water and a very few other exceptions, take up the least volume in the solid phase. Most things, when they go from a liquid to a solid, okay, what do we call it when we go from a liquid to a solid? Freezing. See? So another way to say this is when most things freeze, they take up less space. They become more compact. They become smaller. So if I have a given amount of some substance and it's in a liquid form and I freeze it, I take my ice cube trays and I fill it with this substance. It's a liquid, and I put it in the freezer. Will the ice cubes be smaller or bigger than the ice cube tray? Smaller, right. The same amount of matter will take up less space. They will become more compact. They'll become smaller. That's true for most everything except for water and a few other exceptions. Now, I just have to ask this for my own curiosity. How many people in here still fill ice cube trays? 1, 2, 3. Okay. So there's 3 of you that know what I'm talking about here on filling ice cube trays. This is one of those common reference points that I realize that most people don't understand anymore. When you fill up your ice cube trays, just realize if you fill them all the way to the top, when they freeze, your ice cube is actually going to be bigger than the ice cube tray. And if you want to have something that's perfectly the right height, you've got to fill your trays a little bit lower, so when they freeze, they'll come up to the top. Now, other people know stories like, for example, I have a soda, pop, Coke, whatever you want to call it down here. I have this, right, carbonated beverage that is too warm, so I stick it in the freezer to cool it down fast, and then I forget about it. What happens? It breaks the bottle, right? If it's primarily water, if I put water in the freezer, let me just think about water. I said carbonated beverage. Let me back off on that. Let me go with something simple. Let's use the water example. If I put water, and remember the carbonated beverage is mostly water, so the same thing happens, but we'll keep it pure to water. If I put water, I've got a bottle of water, it's room temperature, I really want cold water. I'm not going to take the time to wait for it to get cool in the refrigerator. I put it in the freezer and I forget about it. What happens to that bottle? It breaks. The water inside expands and it deforms the bottle. Okay? It's because water in the solid form takes up more space than it does in the liquid form. When you take water and you melt it, it takes a larger space, but when you melt it, it takes up less space. Virtually everything else in the world, when you melt it, it takes up more space. Water is the exception. So, most substances take up least volume in the solid phase, meaning if I've got most things, I have a small amount of it. When I melt it into water, I need more volume to hold it. If I take it from there into a gas, it takes up even more volume. But when I take water, and here's its liquid form, I have more room for the solid, less for the liquid, and then more for the gas. It's kind of a different relationship between those things. So for most things, it takes up a little more volume in the liquid phase than the solid phase. When I have most substances and a solid and I melt it, I need to take up a little bit more volume. I need a container that's a little bit bigger to hold the liquid than I do the solid. But when I keep pressing and I go to the gas, this has the most volume. Here's the physical way to think of this. When I have most things, except for water and a few other things. Except for water, this is what happens. Right up here, see? I've got solid, liquid, gas. It's a direct relationship. From solid to liquid to gas. Solid takes up very little volume, liquid takes up more volume, gas takes up a lot of volume. Okay? If I take something that's gaseous, it's really big, and I cool it down, as it cools, it's going to change phase from a gas to a liquid. It's going to go from big space, that same amount takes up much less space as a liquid. And then I freeze it, it takes up even less space. Okay, so for most things, that's the relationship. Except for water. Water takes up space as a solid, takes up less space as a liquid, and takes up more space again as a gas. Now, that is kind of significant. Because we're going to talk about densities in a little bit, but because of this, it's called hydrogen bonding. And hydrogen bonding is one of the things that causes water, it is the thing that causes water to take up more volume as a solid and less as a liquid. What happens, we'll talk about density later, but kind of jump ahead with the discussion, we'll go back to it again. It's because of this property of water that it takes up more volume when it's solid, which makes ice float. Ice floats because it takes up more volume for the same amount of water, which decreases its density. So for right now, the exception for water, the fact that solid ice takes up more volume than liquid ice, is the reason why ice floats. Why is it significant that ice floats? Let's go back to biology for a minute. Let's say that you're at a pond in the summertime and you're hearing all those frogs and seeing all the fish, you know, and you're just enjoying the day there. And you say to yourself, man, I better enjoy this while I can because winter's coming. And when winter gets here, what's going to happen? It's going to freeze over, right? Why doesn't it freeze under? It freezes over. It doesn't freeze under. And that's the key. You said it freezes over. When it freezes over, the ice holds heat in. Water freezes from the top down, meaning occasionally a pond will freeze solid, and all the living things in there will go and get stuck like that for several months, and when they thaw, they're dead and they become fertilizer on the bottom of the pond, right? But for most ponds, they freeze over and underneath is liquid. See, if it froze, if ice sank, it would continually sink to the bottom and keep pushing all the living stuff to the top until it all froze on the surface. The fact that ice floats means it forms a freeze over the top, and it can freeze down solid, but what it tends to do is hold energy underneath it, which keeps it liquid, which allows things to live through the winter. See, because if water didn't float, everything that lived in water would freeze every winter. The fact that it floats, has a less density, means that it provides a protective barrier. It allows a space where things that live in liquid water can survive the winter. And yes, it gets very cold. But as long as there's water down there, the temperature has to be at least 32 degrees. So if the organism can live in freezing temperature water and the water doesn't freeze solid, then living things can survive the winter. And they can start next year, not brand new, go out and have to restock every pond with fish and frogs and everything else. But whatever survives the winter starts the next spring in place, and it builds from there through the year. Okay? So the fact that water freezes, takes up more volume, makes it less dense, brings it to the surface, and allows many other things too, but this is just one to help you remember it. Why is it significant? And also hopefully helps you remember that ice floats. I mean, more than just your glass of iced tea. In real life situations too, the ice floats to the top. It doesn't sink to the bottom and freeze solid from the bottom up. It freezes from the top and holds energy underneath so that things can survive the winter. Question for you on your own 6-2. Natural gas companies store and transport natural gas as a liquid even though they deliver it to their customers as a gas. Why? I mean, you're going to take your camper, going out, you know, you got to take your, let's say your propane tank. It's another example. Go ahead. Exactly. I can take a freight car and fill it up with many times more natural gas molecules if they're liquid than I could if they were in gas, right? If I can take it as a liquid, then I can, and it becomes a liquid. Natural gas is naturally a gas at standard temperatures and pressures. Like in our room right here, if we had a handful of natural gas, it would very quickly be gaseous form. But if I can contain it and bring it under pressure, and a combination of pressure and temperature, but primarily pressure, I can convert it from a gas into a liquid. I can take this much and compress it into this much, which means I need fewer railroad cars to carry it. I need fewer gas trucks on the highway to transport it, because I can take it from something that takes up a lot of space. The same amount takes up much less space if I change it from a gas to a liquid. And then when I get it to where I need it to be in its small form, and I release it, and my customer needs it in the gaseous form, I just take it from a highly pressurized situation. Send it through a process where the pressure around it decreases, and when it decreases, it changes from from a liquid to a gas. And by the time it gets to my customer, it's in a gaseous form. That's why propane, LP, liquid propane, right? You get it in your tank in a liquid form, but yet when it comes out of the nozzle, it doesn't come out as a liquid, it comes out as a gas. What's happening is the pressure inside the tank is keeping it as a liquid, but as soon as it comes out into the atmospheric pressure, it turns into a gas. You burn the gas, you don't burn the liquid. Because as soon as it's in atmospheric pressure and temperatures, it changes its form, its phase, from a liquid to a gas. and we burn the gas, not the liquid.